Ladies and gentlemen, if I didn't get a chance to say good morning as you walked in, good morning. Hopefully all is well. Today we'll kind of start like we started the last 2 days with another warm-up. So if you want, you could pause the video, have everybody try it. It might take a minute or two to scratch out a solution for this. But just looking at it, do people remember what the idea is or what the topic is that they're trying to ask? They're going to try to ask us to integrate 7x over the quantity of 2x minus 3 and x plus 2. Does anybody know what topic this is? So we'll give it a second. Anybody know? Yes, this actually is partial fractions and partial fraction decompositions. So can we break this up into some pieces with A's and B's and try to find out what A and B are by doing a little bit of algebra. So if you want, let's go ahead and pause the video, give everybody a chance to try it before I show the solution. All right, hopefully you got a chance to try it. So looking at the solution, it would look something like this. Again, partial fraction decomposition starts by taking the denominator and the quantities that we have in the denominator and breaking them up into pieces. So the first piece was a over the quantity of 2x minus 3. The second piece was b over the quantity of x plus 2. And again, we have to multiply by a FFU or a fancy form of 1 to get them to have common denominators, and do a little bit of sneaky algebra by picking some specific x values that when you plug them in will cancel out some of the variables and help you solve for the other ones. And if you do it accurately here, you'll get a b value of 2 and an a value of 3. So if you take that and put it back into the original, and then you do an integral, so in this case you'd have 3 over the quantity of 2x minus 3. You could pull 3 out in the front of the integral. You'd be left with 1 over 2x minus 3, which means you could do u sub in this kind of a case, but then just know that du would be 2. So in this case, if you solve for dx, you would have du over 2, and that's why 1/2 comes out with the 3 as well. So this would be a common mistake that some people make, is not having 3 over 2, but just having 3 there by itself. If you go to the second integral, you'll see that it's just 1 over the quantity of x plus 2 once you pull that b value of 2 out. Then if you let u be x plus 2, then du in this case would be just 1. So that way it's not impacting the coefficient on in front, because in this case it doesn't have a coefficient other than 1. So I'm thinking a final answer would be A, 3/2 the natural log of 2x minus 3 plus 2 times the natural log of x plus 2, of course, plus C. All right, feel free to pause the video if people want to talk about it or take a picture. Otherwise, let's continue on. So we are going to talk about the first portion of section 8.10 today. We are going to be skipping section 8.9. That's actually an optional section that doesn't have too much that's going to pertain to what you guys need to know. So we're going to stick to the script and focus on the main things that you guys need to know for the test in May. So it turns out in section 8.10, we're very close to being done with Taylor and Maclaurin series and infinite series. There are a few other topics that we need to talk about that are kind of short. So we are getting closer and closer to the end. You could argue that this is kind of like the last section about series before we kind of move on and do some things with parametric, doing some things in polar, which you remember those like flower petal graphs and the cardioid graphs or the heart graphs, and then we'll have to do some things with vectors. So let's talk about section 8.10, which is Taylor and Maclaurin series, which of course we know some things about, but then we're also going to say some things about power series and how they work with Taylor and Maclaurin. Of course, since this is the last section, we also get to see some more shortcuts, which will help save us some time in some other situations. So the section starts by reminding us what Taylor and Maclaurin series are. So in this case, it tells us the form of a convergent power series. And if you look at that first box in theorem 9.22, the form of a convergent power series, you'll say, yeah, it looks kind of like what we would expect for building a Taylor series. We're going to need some derivatives. We're going to need a center if there is one. We're going to need some factorials. So basically, we're going to need those two columns, the function and all its derivatives, and then plugging in the center and trying to find out what are those derivatives evaluated at the center. If you look down below, you'll see the definition of Taylor-Maclaurin series, which again is something that we do know. And again, the main differences for Maclaurin series is just more specific. It has a center of 0, or in a Taylor series, it has a non-zero center. So how about example number 1? It says forming a power series. So it gives us the classical two columns, and it does say, can we use the function sine of x to form a Maclaurin series? So because it says Maclaurin series, we're under the assumption that the center is going to be 0. So that's why when we do the two columns, or what we've been built here with the two columns, we can see in the second column that they're going to evaluate all of the function and its derivatives at 0. So at least it's less tedious that everything's listed out for us. So what about f of 0? What is sine at 0? Without looking at the unit circle, hopefully you'd be able to say sine of 0 is 0. Let's just keep working our way down the line. How about f prime at 0 or cosine at 0? Well, that would just be 1. How about f double prime at 0? Well, negative sine of 0 is negative times, or negative 1 times 0, which is still 0. How about negative cosine, which is the third derivative at 0? Well, that's going to be negative 1. Of course, the next one is sine, so it's going to be 0 again. And then it starts to repeat itself. Cosine at 0 is 1. So if you look here, you can actually notice that all of the even derivatives, as well as the function itself, you could argue that's the 0th derivative, are all going to be zeroed out. And the only ones that are going to stick around are going to be the odd ones. And this actually makes a lot of sense. We've already said before that sine of x is odd, so only the odd terms will stick around. So in this case, if you go through it, you could say, well, what do I know about sine of x? I can make a polynomial or power series if I wanted to, and I can make it any degree that I want. I can make it in terms of x. Since I know that it's odd, I can say I can skip the first term because I know that part went to 0. I know the first derivative at 0 is 1, so I'd be left with 1 over 1 factorial. And then because we're doing a Maclaurin series where the center is 0, this would be x to the first. We wouldn't be subtracting any center. And then it does alternate sign. We can see that the second term is also going to be gone because it goes to 0, but the third one is now negative. So then we would have negative 1 over, and now this would be 3 factorial x to the third, again because the center is at 0. We can also see that we have the fifth one, and it's positive, so 1 over 5 factorial x to the fifth. What about the next term in line? Well, we know it would be alternating sign, so it would be negative. How about 1 over 7 factorial, and then x to the 7th? Now let's go plus dot 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 to say this pattern continues. But then how could we write a generic term for sine? So in this case, we have to think a little bit, but we've talked about it a lot in Algebra 2, and I think we've even mentioned it in this semester a few times already when we're talking about factorials and doing some reducing with different quantities that we have. How do you write a generic odd number in algebra? Well, there are two ways you could do it, but maybe the first thing we should address is the alternator. We can see that it goes from positive to negative to positive. So my first question for you would be, how can we write alternator that starts positive and then goes negative? Anybody know? Well, we'll definitely need negative 1. And then usually people will say it's either going to be to the nth power or to the n plus 1. In this case, it's going to be to the nth power. And the reason being is because we want the first term to be positive. If you wanted the first term to be negative, we could raise it to an n plus 1 power, and that would actually get the negative done for us. So then now how about x? Well, x is going to be raised to an odd power. What is a generic way that you can write an odd number in algebra? Remember, there were two ways you could do it. Anybody remember? Two ways you can write an odd number. So we said in algebra you could say 2x plus 1, or you could also say 2x minus 1. And the reason why it works is because how do you write a generic even term? We know a generic even term can be written as 2x. So then if we add 1 to that, 1 unit more than an even number will be guaranteed to be odd. And using that kind of similar logic, you could also say that 1 term less, or 1 unit less than an even number would also be odd. So one that we're going to run with is going to be the 2x plus 1. I think I mentioned to you guys this before as well, is that we always want to choose the next one in line, especially since we're talking about sequences in series. Wherever we start, we kind of want to move in the positive direction to the right. So that's why I'm choosing 2x plus 1 instead of 2x minus 1. So in this case, since we're talking about n values instead of x values, I'm going to go with x to the 2n, and then this will be plus 1. Now we also know there has to be a factorial, but if you take a look at the terms that we have written, doesn't that factorial have to match up with the exponent for x? So in this case, like let's say I was looking at the third term. Wouldn't this 3 factorial match up nicely with the exponent for x here? So if we have a generic exponent of 2n plus 1, then what has to be the factorial down below? It would have to be the quantity of 2n plus 1 and then a factorial. So in this case, we could say that this is the generic term for what sine would look like. So if you wanted to, you could label it on your notes. You could say this is going to be the generic term. So just a small extension on some things that we know. What are some other things that we could say? Like I said, in algebra, we know how to write odd numbers. We also know how to write even ones. And if we actually went through and did the ratio test on this one, this generic term that we have here, the ratio test would tell us that this series converges for all values of x. So if you wanted to, you could write it. You could say by the ratio test. So if we were to do it here, it would actually tell you that this series converges for all values of x. So this means that if it's convergent for all values of x, that all values of x in this polynomial that we're creating down here are going to match up really nicely with the function, and they're going to be exact, which makes the series that we've created a power series because it's no longer an approximation. It's going to be an exact representation or a different representation of the exact values of the function itself. Okay, so that's kind of nice. Starts with something that we know and just builds on a couple little tiny things that we can add in as well. So that's example number 1. So the next thing the book says is talk about the key points. And if you want, you could read that paragraph that's there. I kind of want to just look at the theorem. So theorem 9.23, convergence of a Taylor series. It says if the limit as n goes to infinity of r sub n is equal to 0. Ooh, does anybody know what this means? The limit as n goes to infinity of r sub n is equal to 0. What does r sub n mean? Well, if you remember, r sub n was the remainder. So this is saying as n gets really, really large and the remainder is going to 0, well, if the remainder is 0, then what does that mean about your approximated value and the exact value? Well, if the remainder is 0, that means your approximated value and the exact value are the same. When you subtract them, when you find the difference, if they are not different, then the remainder is 0. So in this case, it's saying that the series that you're creating is going to be a power series and is actually going to equal the function itself. So that's what it means when it says the Taylor series for f converges and equals f of x. And then it gives us some generic notation for how we can build these Taylor series. Of course, this top part is talking about the slope evaluated at the center. Here we have the classic factorial, x minus the center, and notice the power of n matches the factorial down below. Okay, so then in example 2, we're actually not going to do, it says show that the Maclaurin series for the function sine of x converges to sine of x for all values of x. So it's kind of like a proof. So again, I'm kind of sticking to the things that we absolutely need right now. So if you want, you can actually cross that off. But instead, don't just block out that space. I want to use that space for something else. I want to use it for the main 3 functions that have made an appearance for us. And we can also talk about them in terms of Maclaurin series. We just mentioned sine a second ago. We said that sine was odd. So I want to make sure we associate sine with being odd in our minds. So what would the series look like? Well, it would be x, and it would be minus technically 1 over 3 factorial. And this x should be 1 over 1 factorial, but we know that 1 over 1 factorial is just 1. So the next one will be 1 over 3 factorial times x to the third. Or if you wanted to, you could write it as x to the third over 3 factorial. The next one, we know it's alternating sign, so it's going to be positive. It's 1 over 5 factorial x to the 5th, which we could write as x to the 5th over 5 factorial. How about just one more for good measure? We got minus because we know it's alternating sign x to the 7th over 7 factorial. And if we keep going down the line, do you remember how to write the generic term, or have you already forgotten? Well, we know it needs to have an alternator, and we know the first term needs to be positive, so it'll be negative 1 to the n. We have x to the 2n plus 1 because that's the generic way to write an odd number. And then since the exponent has to match up with the factorial, we know the factorial will be the quantity of 2n plus 1 as well. So how about these other two? So these other two have shown up before, but maybe we haven't talked about them yet today, so that would be something to mention. How about e to the x? The way that I like to remember e to the x is like a prototypical, like your stereotype, the first power series that you would think of, the most generic one where everything kind of works out perfectly and nothing's too fancy. So the way I think about it is that it doesn't alternate sign, and it does kind of go in order. It doesn't have any missing terms. So just kind of going down the line, it'd be like 1 plus, technically that's x to the 0 over 0 factorial. And then the next term in line would be like 1 over 1 factorial x. So I guess I'll write it out. So 1 over 1 factorial and then x to the first. After all, it's Maclaurin, so we're not expecting to see any x minus any centers. The next one would be 1 over 2 factorial and then x to the second. Again, it doesn't change sign, so how about 1 over 3 factorial and then x to the third? maybe now you see what I mean by like prototypical, stereotypical. What would you expect these kind of power series to look like? So then my challenge to you would be, if we just have this continue on, what would the generic term look like? Well, would we need an alternator? No, we wouldn't need an alternator because we know all of the terms are going to be positive. So then really, how can we get to the next term in line? Well, we could take 1. We could divide it by the factorial that matches up with the exponent. So how would you feel about 1 over n factorial times x to the n? And if you wanted to, you could say, well, if I take 1 over n factorial and multiply it by x to the n, isn't that the same thing as x to the n over n factorial? And it turns out that is the generic term for e to the x. So this would be kind of like your standard kind of a series. That's the way that I always remember it, or the most basic one. Except basic nowadays means something different than it used to. So, all right, so we have e to the x, we have sine of x. The other one that I would say is pretty important is cosine. And we know something about cosine as well, but we haven't mentioned it today. We know that if sine is odd, then cosine is even. So in this case, we're going to have all the even terms, and we're not going to have any of the odd terms. So then what should this one look like? Well, it should start off with the 0th term, or x to the 0. So in that case, it should be positive 1. We know it's also going to alternate signs, so then it's going to be minus. We know it's going to be even, so once we get past the 0 power, we can skip the first power because the first power is odd. We would then have 1 over 2 factorial and then x squared. Again, we're not subtracting any centers here because it's Maclaurin. We know the center is 0. We know it's going to alternate signs. The next one's going to be positive. The next even that we have is going to be 1 over 4 factorial and then x to the 4th. We know it's going to alternate sign. So how about 1 over 6 factorial, x to the 6th. About one more for good measure, 1 over 8 factorial. We know it's going to be positive, and it's going to be 1 over 8 factorial x to the 8th. So then my challenge to you is, how would we write the generic term? So if you want, you can pause the video. You can have everybody chat for a second. How would you write a generic even term for this cosine? All right, well, we are going to need an alternator. So then notice that the first term is positive. So very similar to what we did in sine with the negative 1 to the n, we're also going to need negative 1 to the n here. Notice that both of the first two terms in both sine and cosine are positive. So then times, well, what do we know about x? It's being raised to a generic even number. So this would be x to the 2n, right? 2n is just like 2x in algebra. How would you write a generic even term? Well, we know we can multiply it by 2 because all even numbers are divisible by 2, which means they're also multiples of 2. We know that the exponent for x in cosine matches up with the factorial down below, so I'm hoping that you would agree the factorial down below is going to be the quantity of 2n factorial. So this would also be the generic term for cosine, which is kind of exciting, because now if we know these things, we can actually use that to our advantage and speed some things up. So you could argue this is one of the main shortcuts that we'll see at the end of chapter 8. All right, feel free to pause the video, chat with each other, or rewind, replay, whatever you need. Sorry if I keep saying that, just trying to make sure that people are comfortable and not just going through the motions. So on this slide I would have filled this in, but we've already talked about the generic terms, so I'm going to keep rolling. So I think in your notes you'll also see some pictures about convergent Maclaurin series, show some pictures about sine and the polynomial that we're creating. Hopefully you would agree that as the polynomial gains in degree, it actually becomes a lot better of an approximator for sine. So if we let it go out to an infinite, if we let it be an infinite series that goes out to that generic term, wherever that generic term is, it actually turns out that it will be exact. Okay, so then the next thing that shows up in the notes are some guidelines for finding a Taylor series. We know how to find Taylor series, so let's see what happens. Another thing that also shows up here is a statement that says the direct determination of Taylor or Maclaurin coefficients using successive differentiation can be difficult. And the next example illustrates a shortcut for finding coefficients indirectly using the coefficients of a known Taylor or Maclaurin series. So what this is trying to say is that sometimes it's hard to build those two columns to make a Taylor or Maclaurin series. Sometimes the derivatives can be very challenging or very tedious to find. And then sometimes evaluating the function and the derivatives at the center is not necessarily an easy thing to do. But what you can do is use your knowledge of some of the main players when it comes to power series, like e to the x, sine, and cosine, and use something that you know for algebra to make your life a little bit easier. So MC hammer would have been the GIF or the GIF here, however people want to say it. So how about example 3? A perfect example of a nice shortcut that we now can use when we want to. So it says find the Maclaurin series for this function sine of x squared. And notice it's not sine times x squared, it's sine of x squared. So immediately, what could be the issue with doing 2 columns? Can you see what the issue might be? If I try to take derivatives of this function, what old friend am I going to run into? Well, I'm going to run into chain rule. And maybe the chain rule is what's going to make it more challenging to find the derivative. And maybe that would be something that we could do a lot faster in a different way. So what I would do is kind of talk about the composition that you see. I see that x squared is inside of sine. So let's start with the outside function, sine, and it turns out that sine is something that we know. We know that sine is one of these power series that we're familiar with. We know that it's odd. So if I was saying something about sine, I would say, okay, I know sine is odd. So if I want to put down below just to convince myself. So I know that it starts with a positive x, technically 1 over 1 factorial, minus, because I know it alternates sign, x to the third over 3 factorial. We can list out a couple terms. I know that it changes sign, so then x to the 5th over 5 factorial, and then minus, how about x to the 7th over 7 factorial? How about the generic term? Have you forgotten already? Now that I've asked you the 3rd time, I imagine you didn't. This would be negative 1 to the n, and then times x to the 2n plus 1, all over the quantity of 2n plus 1, and then factorial. So then we know this about sine. We know this composition is saying just take x squared, and what did x squared do? It replaced x. What normally was just sine of x is now sine of x squared. So the cool part about this shortcut is if we know that sine is odd, and it has these terms that are right here, then if we want to find out what sine of x squared is, all we would have to do is just replace the x with x squared for every term that we see x. So this first one is just x, so then I would replace it with x squared. In the next term, I would replace x with x squared, and we're raising it to the 3rd power, and now it's over 3 factorial, plus x squared, so we're going to be raising that to the 5th, all over 5 factorial, and then minus x squared to the 7th, all over 7 factorial. We can even do it for the generic term. We can say negative 1 to the n, and then we can say take x squared and raise it to the power of the 2n plus 1 quantity all over the quantity of 2n plus 1 and then factorial. So let's simplify it just a touch. So in this case, we could say for a final answer, sine of x squared starts with x squared minus, how about x squared to the 3rd? Do you remember when you take exponents of exponents, what operation? Well, it's going to be multiplication. So that will turn into x to the 6th over 3 factorial. We just go down the line. How about x squared to the 5th power? Well, that would be x to the 10th over 5 factorial minus x squared to the 7th. That's x to the 14th over 7 factorial. And if I go down to the generic term, I have negative 1 to the n. Again, I can do the same thing here. X squared to the 2n plus 1 power. If I wanted to, I could multiply the 2 and the quantity of 2n plus 1. How would you feel about x to the 4n plus 2? And of course, the denominator still stays as the quantity of 2n plus 1 factorial. So that might seem like a lot of writing, but if you think about the other way to do it, where you build the 2 columns and have to build it out that way, I'm thinking this saves us a bunch of time. So hopefully this is enough to say it's in our benefit to know something about sine, cosine, and e to the x. Obviously this one is just for sine, because that's the only example that we had here in example 3. But a very similar conversation could be had if this was cosine of x squared. Or what if it was e to the x squared? You know, you could start with those generically and then plug in what you need to after that. So I think that's a very nice trick that actually is something that makes a lot of sense. So then the book wants to remind us to be sure to understand the point that's being illustrated here. Because the direct computation of Taylor-Maclaurin coefficients can be tedious, by that I mean the 2 columns, the most practical way to find a Taylor-Maclaurin series is to develop a power series for a basic list of elementary functions. What this means is, can we do the same thing that we know about e to the x, cosine, and sine? Can we do that for other functions? And if we had a short list of functions and their generic power series that are associated with them, then couldn't we do this trick where we're just starting with those and then plugging other things in for other kinds of functions and other kinds of questions? Of course. So from this list, you can determine power series for other functions by the operations of addition, subtraction, multiplication, division, differentiation, integration, or composites, which is just functions inside of functions. So if you go through your notes a little bit, I'm not sure exactly where it's at. It might be in the next page, but you'll see this large gray box that has some functions in there. So I'll give you a second to try to find this in your notes. It shouldn't be too far away. So once you find it, you can go ahead and flip to it. You'll notice that the three right in the middle, e to the x, sine of x, and cosine of x, are the ones that I've already mentioned. Those are kind of important. I would say those are really good ones to know. The next, I would say those three are probably the most popular with questions that we might see in the future. Ln x would also be the next one, so maybe I would consider that to be the next one to maybe kind of know. And then the one that we're going to be discussing tomorrow is going to be the one here on the bottom. So that would be something good to know. I wouldn't commit all these to memory. I think mostly e to the x, sine, and cosine would be pretty good. If you could do natural log, I would say that's in your advantage as well. It's not terribly hard to come up with. If you look at the power series, it's not super extravagant or exquisite. So I would say those three plus maybe those other two that I have arrows next to. Okay, so then of course I have some bonus examples like I have the last couple days. So if you could pause the video, that would be great. Give everybody a chance to try these 4 questions, maybe on a separate sheet of paper, somewhere where you can do a couple examples, talk to some other people, and see what happens. So what about these right here? What do you think would happen for these? And then please don't do this with 2 columns. Please try to do it the way that I just described, where you're starting with one of the main 3, e to the x, cosine, or sine, and doing some things with algebra for plugging in. This is the shortcut. This is what will make your life easier. So let's go ahead and pause the video, give everybody a chance to try it before I talk about the solutions. All right, so we're just going to go right in order. The first one that I have is e to the negative 3x. So notice that here we just started with e to the x, which is the prototypical kind of a power series. Again, nothing's missing. It's not alternating sign. And then all I have to do is replace all the x's with negative 3x. So this first one, I'm going to plug in negative 3x. That's why it shows up as negative here. What if I take negative 3x quantity and I square it? Well, then negative 3x times negative 3x is positive 9x squared. How about if I take negative 3x and I cube it? Hopefully you'd agree that's negative 27x cubed. What if I take it to the 4th? I can keep going. It's going to be positive 81 and just kind of working my way down the line. Basically, I'm just taking negative 3x and replacing it for all the x's that I know inside of the power series for e to the x. So hopefully you got something like this. If you're interested in the generic term, you could also write the generic term down. So if I took that x and replaced it with negative 3x, the book even does one better and shows how to break that up into the pieces. Since you have negative times 3 times x, that's basically like negative 1 to the nth power times 3 to the nth power times x to the nth power. Okay, so that's the first one. How about the next one, cosine of 4x? Again, cosine we know is even. So this is the generic even cosine. We know it starts as positive and alternates sign. So all we would have to do is just go plug in 4x for all the x's. So notice the first term is going to have to stay as 1 because I'm not plugging anything in. How about the next term? It's minus. So that would be something to note. And then I take 4x and I square it. Well, 4x times 4x is 16x squared. But notice how it's still negative. The next one in line is x to the 4th. Again, 4 to the 4th is 256. And this will be x to the 4th over 4 factorial. And notice how that one is positive. So basically the same idea, just kind of working this way down the line. Again, if you're also interested in doing things with the generic term, you could copy this part down and what it comes into. Again, you can pause the video if I'm going too fast and take a second to write it, or you can take a picture if you'd like to. There's nothing wrong with that. Okay, how about the next one in line? They have cosine and then x to the 3/2. So notice that x to the 3/2 is on the inside of cosine. We know that cosine is even. We know that it's even. It starts positive and then alternates sign. So all we would have to do is just go replace all the x's with x to the 3/2. And if you do that, so you can actually see some terms here on the bottom. Here's what the terms would look like. It would be 1 minus x to the 3rd over 2 factorial plus x to the 6th over 4 factorial. Again, if you're interested in generic term, you could write this guy, or you could write the guy right below it. Give you a second to jot it down. Feel free to pause if you need it. And then the last one, how about 2 sine of x cubed? So this one I probably would have done in a couple pieces. I would have started with sine. which we know, of course, is odd. So if you look at this generic term, hopefully that makes sense as to why they're running that. That's the generic way to write a term in sine. That's odd. Now we're going to replace all the x's with x cubed. So then we could do that. And then what I would do after that, once I have all those terms there, then I would go through and just multiply everything by 2. So I would kind of do it in 2 steps. I would say, okay, I know that sine is odd. Then I would find sine of x cubed by plugging in x cubed for all the x's. Once I have maybe 4 or 5 terms and a generic term listed for that, then I would go back through and just multiply everything by 2. If you don't think it's too much to do all at once, then you could multiply by that 2 at the same time as you're finding sine of x cubed. For some of you, that's not going to be a non-issue. You could do all that at the same time. But since it's our first time doing it, I would say maybe just do it in a couple steps. That way you're not messing up some coefficients. I think I've talked to some of you guys before about how coefficients can make the big difference between getting it absolutely right and potentially getting it wrong. Okay, so that actually turns out to be the last example that I wanted to do here today. Give you a small preview of what's to come tomorrow. I want to talk about binomial series. So this is not the first time we've talked about binomial series. It's actually shown up a few times in conversation already this year. It's even shown up in stats class. For anybody that's in my stats class as well, maybe they could tell us where a binomial series shows up or what kind of very famous mathematical object can help you with binomial series. Do you remember? Well, of course, the binomial series deals with Pascal's triangle, right? So Pascal's triangle says if you take a binomial and try to expand it, you can actually expand it using Pascal's. So if you notice, we have a 1 and then a 1, 1. So then this will be how Pascal's is starting to build. Then there's a 1 here, a 2 there, a 1 there. You could keep rolling. There's a 1, a 3, a 3, a 1. And you can keep going down the line. I won't just keep circling the numbers here, but that's kind of interesting. So we'll talk about tomorrow to kind of start here is how could you write binomial series? Those are functions. How could you write them as infinite power series that will give you not just an approximation, but exact values? And if you noticed or paid attention to it when I showed you the first time, if you go back to that little gray box that's in your notes, you'll see that that actually shows up on the bottom there. You have the quantity of 1 plus x to the k. So by definition, 1 plus x is a binomial. We're raising it to a k power, so that means it's a binomial expansion. And if you look at the right-hand side, you'll actually see that that's going to be the infinite power series that we're going to come up with. It looks maybe a little bit scary, but I promise you it is not going to be that hard to come up with. So that being said, if you want, we could pause the video, or in this case, the video is going to finish. The sub could just give you guys the assignment for today. It's going to come from the book again. Just make sure that if you're interested in solutions that you are checking those solutions out on a day-to-day basis to make sure everything's going all right. And then tomorrow we will jump into talking about binomial series and how they relate to infinite power series kind of going forward. So a few of you guys have reached out to me over email. If there's anything else I can do to help you out, let me know. I might not get back to you right away, but I am still trying to help where I can. All right, guys. I hope you have a good rest of your day, and I will talk to you tomorrow. Adios!